previous lessons, we learned how to draw a Lewis dot structure from a chemical formula. And we also learned that a chemical formula may have more than one Lewis dot structure. And the reason why they have multiple Lewis dot structure is because the electrons are delocalized. That means they can move from one place to another place. Today, we are going to look at those structures more closely using the concept of formal charges. Well, a formal charge of an atom based on this formula is basically the number of valence electron, and that is the number of A on the PT. Remember, the number of A gives us the number of valence electron, and we are going to minus the number of bonds surrounding that atoms. But just be careful. A single bond, it has one. A double bond, we have two bonds, right? And then lastly, a triple bond, we have a total of 3. So be careful with that one, okay? And lastly, we have the number of unshared electron. But be careful, this number of unshared electron is not the same thing as the number of lone pair. Because if we have one lone pair, that would give us a total of 2 unshared electrons. So keep that in mind. So that's the formula. For example, let's look at this 2 resonance structure for this same chemical formula. Before we calculate the formal charge of each atom, you need to determine if the electrons are drawn out for us, because that is part of the formula, okay? So in this case, it is not. So we now have to apply the octet rule to put in those electrons. Well, for hydrogen, I know it only needs 2 electrons. So this is already stable. The same thing with the hydrogen over there. And carbon, it has 2, 4, 6, 8. So it's good. And then the same thing here, 2, 4, 6, 8. So that's good. And this hydrogen is the same thing, it's already stable. But let's look at this oxygen. It has that single bond. So it must need a total of 6 more. So there you go. They did not draw that electron there in there for you. So it's going to be tricky, okay? And the same thing over here. Let's go over here. That's hydrogen, that hydrogen. They are all stable because they only need 2 electrons each. But let's look at this carbon right here. It has 2, 4, 6. So how many more electrons does it need? So therefore, this must have a lone pair of electrons right there in order to make it octet. And lastly, we have this oxygen over here. It has a double bond. So therefore, it needs a total of 4 more electrons. So 2, 4. Now it is octet. Now let's go back and apply our formula. Let's calculate the formal charge of hydrogen. So for hydrogen, it has a formal charge of what? Well, the number of valence electrons for hydrogen is 1 because it's in group 1A, so we have 1. And the number of bond, in this case, is just a single bond, so it's minus 1. Does it have any unshared electron? No. Therefore, we just have this 1 minus 1 give us a total of 0. So the formal charge for hydrogen is 0. And notice how this hydrogen and that hydrogen is pretty much the same. So we know right away this must be 0 as well. And that's the formal charge of hydrogen. Now let's go to carbon. So carbon right here, we have the formal charge of carbon, which is in this case, it is what? Carbon is in group 4A, so it has 4 valence electrons minus the number of bonds. This is where it gets tricky. We have 1 for one single bond, 2 right here. So we have 1 single bond here. We have another single bond here. That gave us 2 already. Then we have a double bond. That gives us another 2 more. So we have minus 4. And we don't have any unshared electrons, so therefore it's going to be 0. So the formal charge for this one is 0. And notice how this carbon and that carbon is the same. So right away we know it must be 0 as well. Let's look at this oxygen. Well, this oxygen is in group 6A, okay? So therefore it must have 6 for the valence electron. Minus the number of bonds. In this case, a single bond, so it's just minus 1. But minus the number of unshared electrons. We have 3 lone pair. But how many unshared electrons do we have? 2, 4, 6. So we have minus 6. So what's the formal charge in this case? 6 minus 1 is 5. 5 minus 6 gives us negative 1. So the formal charge is negative right there. Now let's go to this side. I know right away for hydrogen, it's going to be 0 because it looks the same. And over here is also 0 as well. And over here is equal to 0 as well. But one thing changed is this carbon right here, right? In this case, let's look at this carbon. So again, formal charge equal to the number of valence electron, which is 4, minus the bond. In this case, one single bond, one single bond, one single bond. That's a 3 single bond right there. So we have -3. And what about the unshared electron? We have 2 right there. So there you go, -2. And what is it? 4 minus 3 give us 1. 1 minus 2 give us -1. So therefore, this must be a negative form of charge. And look at this carbon. It's pretty much the same thing as that one right there. So I know this must be the same form of charge, which is 0. And lastly, we have this oxygen right here, which in this case, oxygen again is in group 6A. So it's going to be 6 minus how many number bond? We have a double bond that counts as 2. So we have 2 and minus how many unshared electron? Which in this case, we have 2, 4. So therefore, we have what? What's 6 minus 2? 4. What is 4 minus 4? Give us a total of 0. So this must be 0 right there. Now, let's go back to look at the next most important thing on this particular topic. Is that once you determine the formal charge of each atom in the compound, we need to determine which of the two structures are more likely to be occur in this hybrid. There's a hybrid of two structures. And another way of saying that, which structure make a larger contribution to the hybrid? And it's based on two things. First, the formal charge on each atom must be as close as possible to 0. So basically the one that has 0 formal charges will be the one more favorable or more likely to occur. That's the first priority. The second priority is that when you have a negative formal charge, it has to be on a more electronegative elements. Remember, the most electronegative elements are on group 6A and 7A. So be careful with that one, okay? So let's look at this two structures. Well, this one has a negative charge on oxygen, and the rest of them is all 0. And this one has a negative charge on carbon, and the rest of them is all 0. So we have to look at oxygen and carbon. Which one is more electronegative? And of course, oxygen is more electronegative. So therefore, this one is more likely to occur. This one will make a greater contribution. And the reason for this one is that the negative charge is on oxygen, which is more electronegative.